You're about to pour a critical structural element, maybe a column or a foundation. The concrete mix design is perfect. The aggregates are clean. The cement is fresh. But then you see a worker filling the mixer from a murky, on-site water source. At that moment, your perfectly designed concrete has been compromised. The quality of water used in construction is one of the most frequently overlooked factors, a hidden variable that can silently sabotage strength, accelerate corrosion, and lead to multi-million-dollar repairs. So, how do you know if your water is fit for purpose? In this video, we're moving beyond the assumption that all water is created equal. We will walk through the essential tests, from simple field checks you can do in 5 minutes to detailed lab analyses that determine whether your water will create a durable monument or a crumbling liability. By the end, you'll be able to enforce a water quality protocol on your site that prevents one of the most common and costly errors in construction. Let's start with the fundamental principle. Why does water quality matter so much? Concrete gains its strength through the chemical reaction of hydration, where water molecules react with cement compounds. Impurities in the water can interfere with this reaction in two primary ways. They can chemically disrupt the hydration process itself, affecting the setting time and the formation of strength-giving crystals. Or, they can introduce aggressive ions that lie dormant, only to attack the concrete and the steel reinforcement long after it has hardened. The most common culprits are suspended solids, dissolved salts like chlorides and sulfates, and organic matter. The general rule of thumb is simple: if water is fit for drinking, it is fit for making concrete. However, on remote sites or when using recycled water, this isn't always possible, which is why testing becomes non-negotiable. A pro tip from veteran site engineers is to never, ever use water from an unverified source, no matter how clear it looks. Groundwater or surface runoff can contain deceptively high levels of destructive salts. We can break the tests down into two categories: simple field tests for daily checks and advanced lab tests for qualification and troubleshooting. The first and easiest test anyone on site can perform is the visual and smell test. The water should be visibly clear, free from suspended silt, organic matter, and algae. It should have no noticeable odor, especially a sewage or rotten egg smell, which indicates organic impurities that can severely affect the setting time. A slightly more quantitative field test is the settlement test. Take a 1-liter clear glass jar, fill it with the water sample, and let it sit undisturbed for a couple of hours. Afterward, observe if any sediment has settled at the bottom. A significant amount of silt or suspended solids will weaken the concrete paste aggregate bond and increase the water demand, messing up your carefully calculated water-cement ratio. This is a common drafting mistake in specifications, failing to set a permissible limit for suspended solids, which should typically be below 2 grams per liter. Now, let us talk about the two most critical chemical tests you can start with on site: pH and chloride content. The pH of water measures its acidity or alkalinity, and it has a direct impact on the hydration process. A highly acidic or highly alkaline water can retard or even prevent proper setting. The ideal pH for mixing water is between 6 and 8, essentially neutral. You can test this easily and cheaply with pH test strips or a digital pH meter. If the pH is below 6, the water is acidic, which can corrode the reinforcement and etch the surface of the concrete. The second, and arguably most important, quick test is for chlorides. Chloride ions are the primary cause of corrosion in steel reinforcement. As the steel corrodes, it expands, creating immense internal pressure that cracks and spalls the concrete from within. You can use chloride test strips for a rough estimate. Any chloride level above 500 parts per million, or 500 milligrams per liter, is a major red flag for reinforced concrete, and requires immediate investigation and likely rejection of the water source. This is a non-negotiable check for any structure in a coastal environment. When a water source fails a simple field test, or if you're qualifying a new, non-potable source like treated wastewater, you must escalate to laboratory testing. The gold standard comparative tests are the setting time test and the compressive strength test. As per standards like ASTM C1602, you prepare concrete or cement paste cubes using two types of water, the suspect water and distilled or deionized water as a control. You then conduct the Vickett's apparatus test to determine the initial and final setting times. If the setting time with the suspect water is more than an hour different from the control mix, it's likely unsuitable. Similarly, you cast concrete cubes and test them for compressive strength at 7 and 28 days. If the strength of the cubes made with the suspect water is less than 90% of the strength of the control cubes, the water is rejected. This is the definitive proof you need. And it's a pro-level practice for any major project to establish a baseline for any non-municipal water source. Beyond chlorides, a full lab analysis will test for other destructive ions. Sulfates are a key target. Sulfates in water, often from gypsum-rich soils or industrial effluent, react with the tricalcium aluminate in cement to form ettringite. This compound expands within the hardened concrete, causing internal cracking and disintegration, a phenomenon known as sulfate attack. Another test looks for alkalis, specifically sodium and potassium oxides. High alkali content, when combined with certain types of reactive aggregates, can trigger a destructive alkali-silica reaction, a gel-forming reaction that expands and cracks the concrete from the inside out. A common on-site mistake is to use seawater in a pinch. Seawater is a cocktail of chlorides and sulfates. While it can give higher early strength, the long-term durability is catastrophically compromised due to accelerated corrosion and sulfate attack. It should never be used in any reinforced concrete structure meant to last. Finally, we must also consider water used for curing. The same purity standards largely apply. Water with high dissolved salts or organic matter can stain the concrete surface, create unsightly efflorescence. Those white, powdery deposits, and in the case of chlorides, initiate surface corrosion. A pro tip for flawless finishes is to use clean, potable water for curing exposed architectural surfaces. The initial set of tests might seem like a delay, but it is an insignificant investment compared to the cost of demolishing and replacing a failed structural element. Establishing a water quality log for your project, documenting every test result, is a mark of a professional and rigorous quality control system. To summarize the key takeaways: 1. Never assume water is clean. Conduct visual and smell tests first. 2. Use simple pH and chloride strips for rapid, on-site screening. 3. For any doubtful source, mandate lab-based setting time and compressive strength comparative tests. And 4. Remember that curing water quality is just as important as mixing water for a perfect final appearance. Now I want to hear from you. In the comments below, what has been your experience with water quality on site? Have you ever encountered a project delayed or damaged by impure water? Your stories help the entire community learn.